Good day, everyone, and welcome to another Lanfrica Talks series. This is the 10th episode. We are super honored to have Professor Gašper Beguš, Assistant Professor at UC Berkeley, with us today, who will talk to us about modeling language from raw speech in an unsupervised manner, a deep learning approach. Professor Gašper Beguš is an assistant professor at the Department of Linguistics at UC Berkeley, where he directs the Berkeley Speech and Computation Lab. Before coming to Berkeley, he was an assistant professor at the University of Washington, and before that, he graduated with a PhD from Harvard. His research focuses on developing deep learning models for speech data. More specifically, he trains models to learn representations of spoken words from raw audio inputs. He combines machine learning and statistical modeling with neuroimaging and behavioral experiments to better understand how neural networks learn internal representations in speech and how humans learn to speak. Thank you so much for having this talk with us, and the stage is yours.
Thank you so much, and thanks so much for inviting me. It was a real privilege to learn about the Lanfrica community and all the cool things you do. So it's a great pleasure to be talking to all of you today here. So today I want to talk about modeling language from raw speech in an unsupervised manner, and how to do that with deep learning models that we've seen recently developing. Okay, so modeling language from raw acoustic data is a thing that is possible that has been possible only recently. So maybe for the first time in history, we can actually model language from just raw acoustic inputs and model their linguistic representations from phonology to morphology to morphophonology, and maybe even syntax. And not only that, we can also do it in a fully unsupervised manner, which means that the networks learn without our active supervision and in a more similar way compared to what human infants do when they acquire language. So connectionist models of language have a long history, of course. I give you some literature here, but most of them do not operate with raw data. So we already need some level of abstraction already. So for example, if you model language from some extracted phonetic features, that's already some extraction, some level of abstraction, right? So you're already assuming something as a linguist or as a researcher. There's a lot of work on learning morphology and syntax, and they will always operate on text. And so if you're working with text, you're missing that initial stage of acquisition or initial stage of processing, which is how do you get from this continuous physical property, which is speech, into mental representation units, which are, say, phonemes or words or morphemes, okay? So many models out there operate with pre-assumed level of abstraction, and only recently we've been able to actually model language from raw speech, and that is very important. So I'm going to propose a new approach to phonology that basically takes speech and models phonological representations using convolutional neural networks within the generative adversarial network architecture. We're going to talk about that proposal in a second. But before that, I want to spend some time telling you how I think this approach can bring a lot of advantages and what all sorts of things that we can do with it if we decide to model language in such a way. So I'm claiming that this approach allows us modeling language acquisition. I'm going to show you a little bit about that. Phonetic learning, phonological learning, and morphological learning. So basically learning phonology from phonetic data, which is super important because we can model this complex relationship between phonetics and phonology as well. I'm going to argue that we can model both production and perception simultaneously, which is also very important because previously models have focused either on production or on perception. We're just adding articulatory information to the model, so that's something that we're actively doing in the lab right now. We can go higher than phonology or morphology, maybe. Maybe we can even model syntax with these models. I'm also going to talk about an extension of the GAN architecture that I've been working on that is capable of lexical semantic learning. We also can model language change or sound change. And finally, two important things when we want to compare learning in humans and machines, we can directly compare brain outputs so we can compare how brain processes speech and how artificial neural network process speech, and we can compare how they perform behaviorally, right? So how humans perform and how artificial neural network perform on the same task. That's a methodological innovation because we can basically take the same data, train human subject and artificial neural networks and compare their performance. All of that, again, is done in an unsupervised way, unsupervised training from raw acoustic speech data. I just want to spend some time arguing that phonology is really cool and underrated in the cognitive modeling work. So speech and signs in sign language are arguably the only continuous properties of language. They're only physical, measurable properties, but speech is a continuous dimension, right? So it's a physical property, it's continuous, and humans, the first thing in language processing that human needs to do is to turn that continuous space into discrete mental representation units. Okay, so from continuous into discrete mental, from continuous physical into discrete mental representations world, and that is exactly what deep neural networks need to do, right? So they get some data and they need to classify it or just learn representations about that data. And one thing that we have an advantage in speech scientists have an advantage on is that we understand speech and speech acquisition relatively well, and that we can use that those well understood dependencies in speech to basically test these neural networks in a more efficient way, maybe, or in different ways than if you work on vision. And a lot of work on artificial neural networks or deep learning is performed on vision. And here we have this unique data that we understand really well, has dependencies and properties that this visual data does not have. And so it's really cool to use it. Second, I'm going to talk a lot about generative models. And in vision, we don't really have that generative component easily available to researchers, right? So you can dream, you can imagine things, but for me as a researcher, it's going to be very difficult to access your dreams and your imagination. You'll have to draw something. Whereas in speech production or speech generation, we have innate apparatus to produce speech, to generate speech constantly. It's very easy for me to record your speech. And so that generative component is there. And we speak all the time, and we construct new sentences, and we can make up new words. So we have a more direct access to production data in the speech domain versus the visual domain. Okay, so a couple of things I want to do today. I'm going to argue that acquisition of speech can be modeled with deep convolutional networks into GAN architecture. I'm going to show you a technique for retrieving internal representation that are linguistically meaningful. I'm going to propose a model that can learn linguistically meaningful units, so an extension of GAN that is appropriate for linguistically meaningful units. I'm going to argue that we can go higher than phonology, and then that these kind of work, that this line of work has implications for both our understanding how language works, but also our understanding how deep neural networks work, right? So we can learn from on both sides of this spectrum. Okay, and a couple of things we want to pay attention to as well. I'm going to claim that evidence of symbolic-like, rule-like representations or computations emerge in these networks. And this is important because we're linguists and we like rules and we like symbolic systems. And there's a long-standing discussion between symbolism and connectionism. And some of the things that connectionism has been struggling with are discrete or disentangled representation and categoricity. And I'm going to claim that those emerge automatically in these models. And also, I'm going to focus a lot of time on causal relationship between latent space and meaningful units in the output. So we want to understand that causal relationship between latent space and some linguistically meaningful units in the output. Okay, within the brain ANN comparison, I'm gonna go over that briefly because we're gonna probably run out of time. But I would just want to say that these networks also allow you to basically compare brain processing of speech and artificial neural network processing of speech in a more natural, in a more indirect way. So we don't need any transformations. Our models learn in an unsupervised way. We can train them on whatever processing speech we want, and then directly compare representations at different layers in the brain or in the artificial neural networks. So this is again an advantage of speech processing because we have data that does not exist in the visual domain, and a lot of human brain comparison, as you can see here, are performed on vision and significantly fewer on text. On language, and most of them are on text. Some of them are also on speech, but we want to do more interpretable. We want to find more interpretable techniques, not just some linear transformation that predicts, one signal from the other. Again, we want to work on phonology, not only phonetics, in an unsupervised way. And I'm going to propose a new technique to visualize deep neural network that is useful for speech processing in any case. Okay, so I'm going to briefly talk about the model, then we're going to talk about some case studies, and then what can we conclude for that. So the main proposal in this talk maybe is phonetic and phonological acquisition can be modeled as the dependency between latent space and generated data in GANs. Okay, so GANs, very briefly, a relatively new architecture, a generative deep learning in generative deep learning, where the generator takes some latent space, in our case 100 latent variable, uniformly distributed from -1 to 1, and through a series of 5 convolutional layers generates data, speech data, right? So this is the raw audio. That gets fed to the discriminator. The discriminator needs to estimate what is real and what is fake. And then the training data is the thing that the models actually get. For example, timid, you can feed the timid to the discriminator. So the discriminator gets real and fake data. He needs to figure out what is real and what is fake. The generator tries to trick the discriminator into thinking it's producing real data. So at the beginning, the training is the generation is bad, right? So the generator just produces noise, but in training, it gets better and better. At the end of the day, the generator is really good at producing speech-like outputs. Now, there are one crucial aspect of this architecture, and I think the only architecture, the GANs are the only architecture where the generator never has direct access to the training data, right? It never sees training data directly. The discriminator, of course, sees training data, but the generator does not. And that is crucial because now the generator needs to learn by imitation and imagination. And And this is a very different training objective compared to just, say, replicating data. And we're going to see that the networks generate innovative outputs that we can learn a lot from, from the perspective of cognitive modeling. So why are GANs appealing? That's a generative model, so we know we produce speech. The network needs to learn to make some data from noise, right? Again, they don't replicate, but innovate. And the learning objective is quite different from others. And if you think of, humans need to learn to speak, move muscles from audio inputs, right? So the modality is very different, and we don't get the production data directly. So the fact that the generator doesn't see data is actually good. So we have, again, unsupervised learning, raw acoustic data, and to my knowledge, language has now been previously modeled. Language acquisition has now been previously modeled with GANs. Okay, we can start with the simplest thing possible. For example, a small rule in English phonology, allophonic rule, that in old SPE style would be formalized like this, but it's basically the aspiration of voicing. Oh, sorry. The aspiration of voices stops when S proceeds, right? So the English aspiration rule. So we have words like pit, they're aspirated before stressed vowel, and we have words like spit. When the S immediately proceeds, the aspiration is lost. Okay, so you can slice timid for STV and TV sequences at the beginning of the word, and then feed that to the architecture, and you see what you observe. So you can see that the generator learns to produce data that looks very real, very realistic, and you also can see that long VOT, and when no S proceeds, the generator outputs long VOTs when no S proceeds, and when the S proceeds, the VOT is very short. You can test that, and there's a significant difference. So you can say the network probably learns this minimal rule, this minimal distribution. But actually, if you look at the outputs more closely, it's even more interesting than that. So in the S condition, the network does, for the most part, produce short VOTs, but in some cases it produces extremely long VOTs, actually longer than any VOT that it ever heard before. So I can probably even play. So you can hear this long VOT. So this VOT here is longer than any VOT in the S condition and the training data. If you look at the distribution of VOTs in the training and generated data, right? So this is timid. You see in the S condition, VOT is mostly short, but in the generated output, you see in about 12%, you have extremely long VOTs, longer than any in the training data, right? And this is probably because in some cases, the network fails to reduce, shorten the VOT. And if you look at the language acquisition data, this is exactly a stage in language acquisition. So human L1 learners, they start with short VOT, but then they learn the long VOT, right? So all across the board. And for oftentimes they'll produce this extremely long VOTs in the S condition because they fail to acquire the rule, okay? So you can compare language acquisition with stages in these networks. You can also model language change. So this is an example where we start training models not only on, not only on timid, but you can, combine iterative learning and deep learning and have these models be agents in an iterative learning task. So we have the first GAN is trained on timid, the second GAN is trained on the outputs of the first GAN, the third GAN is trained on output on the second GAN, and so on. You can have these generations of GANs where the GANs start learning from each other. And you see that, say, the distribution of the VOT in the S condition gets gradually longer and longer whereas in the elsewhere condition that is more stable, it remains stable. So you can model sound change with this approach as well. Okay, we don't have to stop here. It gets more interested in that. Okay, so this is just distributional data, behavioral data of these models, so to speak. But we can understand better how they're learning these internal representations. So this is a paper that I wrote in 2020, which basically proposes how we can extract, or like how we can find representations of phonemes in the latent space of these networks, and how we can get the causal relationship between those representations and the output. Okay, so as I mentioned, we have latent space, we have convolutional layers, we have the generated audio. And so I'm proposing a technique where to identify variables that correspond to phonetic or phonological features. So basically what we do is we annotate outputs for anything you're interested in. For example, in our case, the most salient thing, but the difference between STV and TB sequences is the presence of S. And you can basically use regression to find those variables that more strongly correspond to S. And if you see, this is the entire latent space, all the 100 variable, some of them have a bigger effect on S than others, okay? Now, for example, this technique identified the 11th variable as the one corresponding to S most strongly, for example. And that we'll see later on basically tells you, okay, this is out of 100 variable, this variable is most likely the one that represents an S. And we can get to the underlying value of these variables with a technique that I'm going to talk about right now. So the relationship between those highly performing variables, or those variables that highly correspond with S, and the probability of S in the output is actually linear. I tested this in a nonlinear regression, and the relationship didn't have to be linear, but it is, right? So on the x-axis, you have the values of Z, 11, right? We know that it's during training, it's uniformly distributed between -1 and 1. And the y-axis is probability of S. So the likelihood of S being in the output. And you see that the relationship is linear. So because of that, we can see, okay, what will happen if I set my Z value outside of this range? Will this linear generalization continue? And it does. And this is one of the crucial things that allows us to basically model language with these networks. So if the dependencies that we observe within the training range extend beyond the training range. And by manipulating those variables, we can control the output and explore the causal relationship between linguistically meaningful units and latent space. Okay, so how do I know that? So I take the 11th variable and set it to some extreme marginal level like -15. Remember, during training, it's from -1 to 1. I set it to -15, and I get like 87 outputs out of 100 that contain an S. Okay, if I set it to -25, it's almost categorical. It's 96. Okay, and it's even better than that. If I then interpolate from that, extreme values, let's say B in the output, to the other side that says don't be the output, the amplitude of S just gradually disappears. You see here that most of the other things remain the same, but the amplitude just shrinks. I can give you an example. Okay, so we have this causal relationship between latent variables and some meaningful units in the output, and I can turn it in and out from the output by manipulating that single unit in the latent space. Okay, so by now you might be thinking like, where is the meaning? Where is linguistic representations behind this? So the technique is very important that I just talked about, to talk to you about. But to model meaning in a more tangible way in these models, I propose a different architecture, a new architecture, not a different one actually, but an extension of it that is based on the information theoretic GAN proposal. But the main idea is that in addition to latent space, the generator now takes also code variables. Okay, so some number of code variables like 100, 010, and 001. That can be one encoded, one hot encoded, or they can have binary codes. And it generates data. And now we introduced a new network that I can call Lexical Learner. And that network is similar to discriminator, but its objectives are slightly different. So the Q network, or the Lexical Learner, takes generated data and needs to figure out what unique code did the generator have when it was producing this particular datum, okay? And so you train the net, so the generator now needs to learn to produce informative data, right? We don't say learn lexical items, we say learn informative data, which means it needs to, take this code and transform it into speech such that the Q network will know what code it had when it was producing it. Okay, the discriminator works in the same way. Now the Q network, can be understood as the perception principle, and the generator can be understood can mimic the production principle. So we have this production perception loop, and learning of meaningful units emerges because we have this production perception loop, right? And the Q network can be then, can just be a classifier, and it is. We'll see that. You can take it away from the architecture and feed it unobserved data, and just classify words, which is nice because that's what what perception is. But anyway, so the important thing here is that the lexical learning happens in a fully unsupervised way. So the network can learn anything about timid, right? It could encode gender of the speaker in these codes. It could encode any property of speech, but it does encode lexical items because they're the most important thing. Sorry, not the most important, the most informative thing. Okay. So that's good. The lexical learning emerges in a fully unsupervised way, and we never say learn lexical item, just because encoding meaning or information in the shape of codes into lexical item is the most informative thing to do. The networks will do that. We also introduce, this is just a more schematic way of representation. We also introduce not only one hot encoding, but binary code encoding, which allows us to basically model holistic lexical learning and also sublexical featural learning, right? So each code can represent a word, but then each bit can represent some sublexical information. Okay, so I trained the network on 10 words, and the network learns 10 words to represent 10 words, the 10 words with unique codes. You can see here in a multinomial logistic regression model, you can confirm that. I also trained them on 8 words in the FIW GAN, so in the featural binary code encoding GAN. And the interesting thing is that the network starts producing novel, unobserved words that are words of English. Okay, so it was trained on these 8 words. Each has about 600 tokens in it. So 8 words, and it starts producing new outputs that it never heard before. For example, start. And I can play an example. Start. So this is a generated output. You see, this is the compare. This is a comparison to timid. And here the data was withheld. The network never saw a start or never saw even an SD sequence, but it learned how to combine things, speech segments, into something that is a word of English. And there are other examples on the YouTube channels. I have carrot and dust. And it also produces SART, right? SART is not a word of English, but it could well be. So it learns a lot about phonotactics and putting things together from a very limited vocabulary at the beginning. Also, I want to talk about categoricity. So remember the first technique when we talked about where you set your values outside of training range and you see the underlying value of an individual variable in these GANs? Well, if you set, say, these binary codes to 15-15-0 instead of 1-1-0, you get almost categorical, one code, one word mapping in the output, which is really nice. In the case, for example, of the word greasy, I get 100% of the time I get the output greasy. So when you're within the training range, you'll have some distribution that's not going to be 100%. But if you set it to, extreme values outside of training range, where and generate from in such a way where your variable of interest overrides all the lower level interaction between these latent variables, you get this nice effect of categoricity and seeing the underlying value of these So this is very noisy at this level because it's generation outside of training range, but you see that in 100% of cases the greasy output is there. So that's good. I also tested how this transferred to entire timid, where we don't work with 8 words only, but with entire timid, and we have clear evidence that it's not perfect, but lexical learning is there as well. Okay, and we also want to explore how the lexical learning works in the perception principle, right, in the Q network. Okay, so this is an interspeech paper from this year. So this is how you test and train the networks. And then during test phase, you can take out the Q network and feed it timid unobserved data, okay? And you see lexical learning happens there as well. So the Q network just classifies words into word identity groups marked with binary code. So that's good. Now you have a generator that generates words, and with the same code, you basically can get classification on unobserved test timid data. And Q network never really sees the timid data during training. So this is good. Also, as I mentioned, we can model simultaneously the lexical learning and sublexical information, sublexical learning as well, right? So, for example, lexical items can be encoded with unique codes, right? So each unique code is a lexical item. But then sublexical information, and we know that the words share, say, phonemes, can be encoded with these features or bits. So each bit can encode a different sublexical, either phoneme or bigram and so on. So again, this is to confirm that the lexical learning happens in GANs, right? So the classification network uses the same code as the generator network to represent words. And we can basically then see how this holistic lexical learning interacts with sublexical information learning. Okay, so this is just an example of how this lexical learning works if you operate with entire timid or like with 500 words from LibreSpeech. So you see that each code represents a word, and then that code represents the same word as well. And this happens in about 20% of cases. Okay, and you see that this, that say the mistakes that the network mislabelings that the network do have a lot in common with the actual word, right? So still, state is, this code is mostly used for still, but the other, words that have it is also state, stand, spoke, stories too, right? So there's obviously some sublexical thing going on. Okay, so we want to know how the encoding works, and if we see any patterns in this featural encodings. Okay, so we trained a network on about 500 words, and you can basically just use transcription of those words when you're passing them through the Q network. Right now we have a Q network that is a classifier. We have raw audio words that are transcribed, and we have code that is the final classification output, right? So what we can do is just say, okay, run 500 words through this Q network, have their transcription and code pairings, and say, okay, have the code as the predictor, and as the dependent variable, and any sublexical information you want as the predictor, right? And we see that, for example, if you take a look at the word initial S, it is encoded with 3 features. So feature 2, feature 3, and feature 5. When they're set to 0, you have a lot of word initial S. When they're set to 1, the drop is substantial. So you have almost no word initial S, okay? And then you can verify that you're actually doing this right. So we have now a system where words are encoded with binary codes, but sublexical information like presence of word initial S is encoded with 3 features. And you can verify that in a causal way with the generator, because you can take those 3 features in the generator, interpolate them from 0 to 1, and you get the causal effect where word initial S just, again, shrinks from the output. So this is basically illustrating how the production and perception can be modeled in these models simultaneously, and basically we can have both components, and the both components actually are necessary for lexical learning to even happen. Okay. So from now on, I'm going to give you a couple of case studies. I'm going to go over this quickly because there are several things you can do with these, combining these techniques that I just showed you. But I'm gonna talk about how we can learn about language and how we can model language properties in language with these techniques. Okay. So first, I looked at the reduplication. Reduplication is one of the most contended properties of language, because some work claimed that you cannot model reduplication with artificial neural networks, and it's a very complex process. And most of the work on reduplication actually, again, operates with features or phonemes. And here we want to see if these networks can handle reduplication from raw speech. Okay, what we did.
Sorry to interrupt real quick, but for some non-technical people here, could you explain what reduplication is?
Yes, absolutely. Sorry about that. Yes, so reduplication is a process that many languages have, where you copy some part of the base and add it to the base. Okay, so if you have a consonant vowel word, reduplication that often, say, in languages denotes plural, is copied, say, first syllable, and have it placed before the base. Okay, so an example, a word like poly. In a word like poly, you take the P, you take the A, and you copy them into papali. You repeat them, or just copy. Yeah, and copying is a complex operation. So we went to a studio, we created about 1,000 nonce words, we recorded them that are reduplicated and unreduplicated. And then for S initial word, we only kept unreduplicated words. So reduplication and S initial words were never there. And so this is our training data. We put it into the GAN, to the CIW GAN. Now, just to illustrate how much more complex this is compared to text, right? So these are text representations of reduplication, like mamai, right? But the networks need to learn from raw audio, and this is a way more complex process, right? Again, we send that data into our CIW GAN architecture. And we see that the network, we gave it to codes 1, 0, and 0, 1, and we hope that it'll learn reduplication. So 1, 0 is reduplication, or vice versa. And it does, actually. If you look at, again, if you go and generate with 5, 0, you see that 98% of outputs are bare. If you generate with 0, 5, 87 outputs are reduplicated. But it's actually even better than that. The network, in most cases, learn to pair unreduplicated and reduplicated forms with the code. And then you can, with interpolation, just turn reduplication in and out from the output, okay? So 1, 0, so here we see 1, 0 or 5, 0 is bare, 0, 5 is reduplicated. And so if I interpolate from 1, 0 to 0, 5, I get from reduplicated to unreduplicated words. Oops.
Secure.
Okay, so this is one example. You can also test now, right? And this is kind of important because you can now say, okay, I'm gonna find how this network represents an S, and I already know how it represents reduplication. So I can wug-test these networks by saying, okay, remember in the training data, S initial words were never reduplicated. So we want to see if the reduplication pattern extends to S initial words as well. So we find how the network represents an S. You see here is a representation. So you identify a variable and you turn that variable to values outside of training range, and you turn the reduplication, the code variable to values outside of training range. Okay, so if the network learned the identity-based pattern, it'll produce Sasara. If it didn't learn, it'll produce something like Nasara, Tasara. It'll just recombine, parts from the output. And it turns out when you force the reduplication and S in the output at the same time, you can basically say, okay, show me a reduplicated S initial form to the network by forcing these two things in the latent space. You get this nice S initial reduplication that was never part of training data. So the first one is the actual generated output. The second is withheld data, human recording, S initial reduplication, and you see a nice parallels between S initial. So S, you see here a period of S, frication, reduplicated syllable, and again S, and it's very similar to the human recordings. Okay, I replicated this experiment as well, and it worked the second time around as well, so that's good. Okay, so here I want to briefly touch on how to do ANN behavior comparison. So we can use these models to compare human performance on any process you want. So in this case, I worked on vowel harmony and devoicing after nasals. I won't go into details about this data, but the important thing is there's a myth that you need a lot of training data for these networks, and it's not true. you can train these networks on very few data points and still get informative results. And what this allows you is to use the same data as we use in artificial grammar learning experiments on GANs and compare directly, ANN, so neural network performance and human performance when they're trained on the same data. We can also follow how they're learning. Okay, so as they're learning, they're producing outputs. There's a technique that I'm proposing in this paper that says, okay, if we freeze the latent space and observe how the outputs work at different training steps, we can see what the networks do with training. And here you see the Zilo gets devoiced into Sulo at 9,000 training steps. And then at 20,000 training steps that they introduce burst and VOT, so they turn an S into a T. So the important thing to note here is that the network, as they're learning, as they're searching through the space of possibilities, they use linguistically interpretable thing, right? They first devoice, then they turn an S into a T. So they use linguistic processes when they're learning and searching through the latent space. And as I mentioned, we can compare the training in directly in human subjects and the generative network because they were trained on the same data essentially. Okay, so now we're kind of moving into a new chapter in this exploration, which is, so we have so far talked a lot about the latent space and data, so the endpoints of these networks. This is an architecture of the generator, and its input is the 100 latent variables, and the output is a second of audio. And in between, we have a series of convolutional layers. And so we are proposing a technique where we can actually understand how these networks encode various phonetic properties in these intermediate layers. And for example, that technique allows us to basically see, okay, if you have a SDV output in purple, how is it represented in the fourth convolution layer, so the immediately preceding convolution layer, and you see that's in orange, and how it's encoded with a layer before that and a layer before that. So the third convolutional layer is in green. You see, we get this frequency following response, so to speak. So green is the output here, purple is the first immediately preceding convolutional layer. You see, all sorts of, we can directly test what information is encoded, what acoustic information is encoded where, and how it is encoded. And that is very powerful. And we can get this nice visualization of how, something like S that arises with our interpolation and silence of a stop and periodic vibration of the vowel is represented at each convolutional layer. You see how basically how we can understand how that transformation towards abstractness works. And the same also for the classifier network, right? So here's the classifier network. We propose a technique for that as well. And that allows us to kind of touch on the final thing, that enables brain artificial neural network comparison as well. So CNNs have been used to compare brain and vision a lot. Sorry, CNNs and vision processing a lot, but less is done on the audio domain and the speech domain. And so we're proposing this technique where we can basically compare the immediately preceding convolutional layer and that we just saw, that I just showed you, and auditory brainstem response. So auditory brainstem response is very deep, is one of the first speech encoding that we can get from the brain. And in a collaborative project, we have this project where we show that the representation of speech in the auditory brainstem response is very similar to the representation of speech in the fourth convolution, so in the immediately preceding convolutional layer. This is, for example, the brain response to a syllable like ba, and we can test how the network, how the CNN encodes syllable like ba, and here are the feature maps that look a lot like ABRs, the auditory brainstem response. And if we sum them up, that is, and summing up or averaging is a very similar process to what we're getting in the brain signal. We get a summarization of electrical activity as a response to some audio signal, and we see that we get a similar frequency following response in the convolutional layer as well. And actually, we're claiming that the way, say, a Spanish trained model and a Spanish trained model and an English trained model have some striking similarities in encoding when we compare them to Spanish monolinguals in the ABR experiment and English monolinguals in the ABR experiment. Okay, finally, this is kind of a preliminary results, but we're adding articulatory information to the model. So where the generator is the same as before, but instead of audio, it generates EMA, or electromagnetic articulography data. So those will be representations of our tongue and lip movements. And then we have a separate pre-trained physical EMA to wave model, and that learning now happens in an even more similar way to what was done before, right? We know that we don't generate speech by just producing sound directly. We generate speech we generate sound by moving our muscles, right? That's the cognitive process here. And this is basically representing that and seeing how articulatory learning happens in an unsupervised way with these models. And you see some preliminary results show quite similar gestures that are learned in the GAN network as they were in the EMA data. And this is, again, all unsupervised. Okay, so I think timing is perfect to stop here. And hopefully, I have shown, or at least pointed to several things we can do with this approach where you model language from raw data with CNNs in the GAN architecture. We can do language acquisition and compare stages there, phonetic learning, phonological representation learning, right? And also morphophonology, maybe even syntax. We have the production aspect and the perception aspect. We can model articulation, as we just saw in this preliminary result model. We learn semantic and lexical and sublexical information. We model language change. And I talked about how we can compare the performance of these networks to the behavior and to the brain representation. So we can basically compare biological and artificial neural computation of speech. And all of that is from unsupervised, in an unsupervised way from raw speech. So to conclude, I think modeling speech data, by modeling speech data with CNNs, we can learn both about how language works and language acquisition works, and also about how these networks learn internal representation. And that is very important. That's one of the most important questions in machine learning today. So there's a lot to do. And if you have any ideas or you want to connect, I thank you for your attention. But if you want to connect more, I have all the papers and code on GitHub and my website. I'm free in email and also available on Twitter. Our lab is on Twitter. And some of the talks and explanations of the techniques and audio samples are also available on my YouTube channel, which has this extremely long address. So with that, I thank you for your attention, and I'm happy to take any questions.
Okay, thank you so much, Prof. Gašper Beguš. We are so honored to have this amazing talk of yours. We definitely will, look more at the work you're doing, look at the other talks and all the papers because there's a lot to learn from here. But thank you so much for coming here and giving us this very amazing talk. We're very, very honored to have you.
Thank you so much for the invitation. It was wonderful, and hope I can, we can stay in touch.
Thank you very much. And I also hope you were able to meet, hear some questions from some African NLP researchers or people in this space. I think many of them also took your email, so they will contact you. Thank you
Perfect.
very much, everyone here and in the online. Thank you for attending this talk. See you all next week and have a great day.
Thanks. Bye-bye.